Hello students, welcome to this video. In today's session we are going to take up a topic that often confuses students yet appears again and across multiple areas of physics, the cavity problem. We will understand what they are, why they appear so often, and more importantly how to deal with them systematically. So let's get started with cavity problems. Now, cavity type questions don't belong to a single chapter. In fact, you will find them scattered all across physics in topics like center of mass, rotational motion, electrostatics, gravitation, and even magnetic effect of current. But in this video, we will narrow our focus to just two areas, gravitation and electrostatics. The reason is simple. The mathematical treatment of both is almost identical. So once you understand how to solve a cavity problem in gravitation, you can apply the same logic to electrostatics as well. The only thing is the symbols will change. In this video, we will take up a series of practical problems to understand the concept clearly. And our focus will be on finding either the gravitational field G, which is small g by the way, also known as acceleration due to gravity if it is Earth, but otherwise we will call it intensity of gravitational field or simply gravitational field and denote it by small g. Or we will have to find out intensity of the electric field denoted by E. Of course, we will be finding out these when a cavity is created inside an object. So by the end of this video, you will have a crystal clear idea of how to approach any gravity problem, whether it is gravitation or electrostatics. Before we begin, let's quickly revise a few important formulas, the ones that form the backbone of our entire discussion. Let's start with the hollow sphere. So let's say we have a hollow sphere of radius r, and here I have written q, that is charge, and m is mass. So depending upon whether you are dealing with electrostatics or gravitation, you will use q, charge, or mass m. And we are interested in finding out the gravitational field or the electrostatic field at various distances from the center of this particular hollow shape. So for example, we would be interested in finding out the gravitational field at this particular point P, which is at a distance small r from the center of the sphere. Please note that radius we will denote by capital R and distances from the center of the sphere we will denote by small r. So if small r is greater than or equal to r, we will use the formula g is equal to gm upon r square is equal to kq upon r square. So that is, the entire shell behaves as if its all mass or charge were concentrated at the center. But what happens when we move inside the hollow sphere where r is less than r? So what happens when r is less than r? G and E both will be equal to 0. So keep this in mind. A hollow sphere produces no field inside it, and outside it behaves just like a point source. What about a solid sphere? When r is greater than or equal to r, the formula remains the same. So this entire solid sphere behaves as if the entire mass or charge is concentrated here at the center. But things change when r is less than r. When r is less than r, we will use these formulas for G and E. Right now we are not interested in the derivation of these formula. The only thing we will note is that you can see over here the gravitational field is directly proportional to small r. Please note G, capital M and R are all constants. Here also electric field is proportional to r. K, Q and R cube are constants. That means as we keep on going away from the center, as small r increases, the gravitational field and the electric field keep on increasing. So inside the sphere, that is for r less than r, the field increases linearly with distance from the center. In other words, if you move away from the center, the field keeps getting stronger until you reach the surface. Okay, at this point it is also helpful to introduce two key quantities, mass density and charge density. So this is mass density, total mass of the sphere divided by its volume, and this is charge density, total charge on the sphere divided by its total volume. Now let's get one step further. What we will do is that I will also give you the formula for r is less than r over here in terms of rho m and rho q. So that's on the next slide. Have a look at this. For r is less than r, this is the formula which we already know. But if rho is given to us, we could use this formula: G is equal to 4 upon 3 pi G rho r, and is equal to rho r upon 3 epsilon naught. Now, what you need to do is note that E is uh, rho r by 3 epsilon naught. And if you remember this, you can easily come to this formula, because what happens is that G, that is the universal constant for gravitation, is analogous to the Coulomb's constant, which is 1 upon 4 pi epsilon naught. So 1 upon epsilon naught is analogous to 4 pi g. This is for electrostatics, this is for gravitation. So what we do is that in this formula, for 1 upon epsilon naught, rho r upon 3, 1 upon epsilon naught, we replace by 4 pi g. So I'll write it over here. So for g, I'll write rho as it is, r as it is, 3 as it is, and 1 upon epsilon naught I'll replace by 4 pi g. And I get this formula: 4 pi g rho r upon 3. Please note that this g is the universal constant for gravitation, and small g is of course the intensity of gravitational field. So please make a distinction between them. Right. I think I have given you enough uh, background to these questions. Please note down these formulas before we get into questions. If you use these methods, you will find that solving questions is not as difficult, and cavity problems are not as difficult as they seem. Let's take up the first question. So a cavity of radius r by 2 is inside a solid sphere of radius r. The center of the cavity is located at distance r by 2 from the center of the sphere. The gravitational field at that point is distance r by 2 from the center of the sphere, lying on the opposite side of cavity on the line joining the center of spheres and cavity. And here g is gm upon r square, and m is the mass of the sphere. So we have been asked to find out the gravitational field at a point P that is a distance r by 2 from the center of the sphere. So we have a situation like this. This is the solid sphere 1, and this is cavity. We will denote it by 2, which has been removed from this main sphere. And in the question, this has been given as r by 2. And we have to find out the gravitational field at point P, which is also at a distance r by 2 from the center of the sphere. This is capital R by 2. R, remember, capital R is the radius of this big sphere. This is r by 2, and this also is r by 2. We have been asked to find out the gravitational field at this particular point over here. So let's begin. So if you want to find out the gravitational field at point P, Gp, then it will be equal to the gravitational field at point P because of this original big sphere 1 subtracted by the gravitational field created by the cavity which has been cut out. So I will call this as G sphere minus G cavity. Minus because we are removing this mass from the main sphere. G sphere minus G cavity. Okay. Now let us put the values based on the formula that we have discussed in the previous slide. G sphere we want to find out at P. Now for the sphere, this point P is inside it. So I will use the formula. This will give me G capital M, mass of the sphere, over R cube into R, which is the distance from the center of the sphere, which is R by 2. So I'll write down R by 2 over here, minus G cavity. For the cavity, for this cavity, this point is outside. So we will use the formula Gm by R square. So G into, now for mass I have to take the mass of this cavity, which will be equal to M by 8. And a little later I'll explain to you how did we get M by 8 divided by R square. What is the distance of point P from the center of the cavity? That is R by 2 plus R by 2. That is R by 2 plus R by 2. So that will be R, and therefore R square. Okay, if you simplify this, we will get Gp is equal to Gm. This one R will get cancelled out. So I'll gain Gm upon 2R square minus Gm upon 8R square. Further simplifying this, I'll get Gp is equal to 8R square is the LCM. 4Gm minus Gm is equal to 3Gm by R square upon 8. And it has been given that gm upon r square is small g. So I could write this as 3 upon 8 g. And therefore, the correct option is 3g by 8. How did we get this m by 8? Let us work on that. We know that mass of a sphere is equal to density of the sphere into its volume, which is 4 pi upon 3 pi r cube. So from this would imply that m is proportional to r cube. And as we can see over here, the radius of the sphere is r, the big sphere is r, and the radius of the cavity is r by 2. So if the radius decreases to half, 1 by 2 times, the mass will decrease 1 upon 2 whole raised to cube times, that is 1 upon 8 times, and therefore we took the mass of this cavity as m upon 8. So this is how we can find the gravitational field at a given point inside the sphere. Before we take up the next question, I want you to explain a, a simpler and a very easy method of finding out gravitational and electric field inside a cavity. So let us say we have this big sphere. We'll call this sphere 1 as big, and this is the cavity which has been cut out. This is cavity which has been cut out, and O1 is the center of the big sphere, O2 is the center of cavity, and the distance O1 O2 is a, small a, and the charge of the charge density is q upon 4 upon 3 pi r cube. Let us say if it would be gravitation, then we would take m upon 4 upon 3 pi r cube. So rho is, let us say, q upon 4 upon 3 pi r cube. Now I want you to keep in mind that E, the electric field inside this cavity, please remember we are talking about the electric field inside this quantity, is given by the formula rho a upon 3 epsilon naught, where a is the distance between the center. So this is a very simple direct way of solving or finding out electric field or gravitational field inside the cavity. Rho a upon 3 epsilon naught. Rho is the charge or the mass density. Please note that a is the distance between the centers and 3 epsilon naught. The most important point to note is that this electric field inside this sphere is constant. As you can see, rho is a constant, a is fixed up, 3 and epsilon naught. So everywhere inside this cavity at any particular point, the electric field will be constant. Similarly, small g, the gravitational field inside will also be constant, and it is given by rho 4 pi a g upon 3. And of course, here rho will stand for m upon 4 upon 3 pi r cube. That care you have to take, that this rho will be mass density. And from this to this, I explained you earlier how 1 upon epsilon can be replaced by 4 pi capital G. So here also we have done the same thing. 1 upon epsilon naught has been replaced by 4 pi G. Rho a upon 3 remains as it is. Lastly, direction of the field. So if let us say this has got a positive charge on it. Let us say here we have all positive charge. I am talking about the electric field, positive charge. Then the direction of the electric field inside the cavity will be from O1 to O2. That means it will be in this direction, O1 to O2. If this were all negative charges, the direction of the field would be away, that is from O2 to O1. So that's another important thing you have to keep in mind. The direction of the field, a positive charge from the center of the sphere to the center of the cavity, in that direction. And if it is negative charge, the reverse. What about gravitational field? Gravitational field, as we know, will be in the opposite direction. So let me use another color to indicate the gravitational field. I'll show it on the very same page. So I'll use the green color. So this would be the direction of the gravitational field. So with this concept in mind and with this formula in mind, what we will do is we'll take up the next question, and you will find that solving that question will be extremely simple if we use this formula of rho 4 pi a g upon 3, or E is equal to rho a upon 3 epsilon naught. So let us move to the next question. Inside a fixed sphere of radius r and uniform density rho, there is a spherical cavity of radius r by 2 such that the surface of the cavity passes through the center of the sphere as shown in figure. A particle of mass mo is released from the rest at the center B of the cavity. Calculate the velocity with which the particles strike the center A of the sphere. Neglect Earth's gravity. Initially, sphere and particle are at rest. And the velocity is given to be this value. We have to show that the value of V will be same. So let us understand this. What do we have in this? So we have sphere 1. From this cavity has been removed. This is the center of the cavity. This is the center of the sphere. And it is given that the surface of the cavity passes through the center of the sphere. That is what we have shown over here. The surface of the cavity passes through the center, and radius of the cavity is r by 2, and radius of the sphere is r. Now what is given is that from this point O, a mass mo is released like this. It will move in this direction. At what speed it will hit point A? So what will be the velocity at point A? That is what we have been asked to find. So our approach will be very, very simple. We are talking of motion from point B to point A. Mass is initially at rest, so I can write down u is equal to 0. And we want to find out v. Now, if I go by the formula v square minus u square is equal to 2as, then u is 0, so the formula becomes v square is equal to 2as. We want to find out v. 2. A will be the acceleration due to, or the gravitational field that is acting over here. So that is inside a fixed sphere of radius r in uniform density rho, there is a spherical cavity of radius r by 2, such that the surface of the cavity passes through the center of the sphere as shown in figure. A particle of mass mo is released from the rest at the center B of the cavity. Calculate the velocity with which the particles strike the center A of the sphere. Neglect Earth's gravity. Initially, sphere and particle are at rest. And the velocity is given to be this value. We have to show that the value of v will be same. So let us understand this. What do we have in this? So we have sphere 1. From this cavity has been removed. This is the center of the cavity. This is the center of the sphere. And it is given that the surface of the cavity passes through the center of the sphere. That is what we have shown over here. The surface of the cavity passes through the center, and radius of the cavity is r by 2, and radius of the sphere is r. Now what is given is that from this point O, a mass mo is released like this. It will move in this direction. At what speed it will hit point A? So what will be the velocity at point A? That is what we have been asked to find. So our approach will be very, very simple. We are talking of motion from point B to point A. Mass is initially at rest, so I can write down u is equal to 0. And we want to find out v. Now, if I go by the formula v square minus u square is equal to 2as, then u is 0, so the formula becomes v square is equal to 2as. We want to find out v. 2. A will be the acceleration due to, or the gravitational field that is acting over here. So that is what we want to find out. And as distance is r by 2, as you can see over here, distance b is r by 2. So by the formula given in the previous slide, we will find out g. So g, as you know, is 4 pi g rho a by 3. So that will give me is equal to 4 pi g into rho. What is A? A is r by 2. The distance between the centers of the two spheres, or the distance between the center of the sphere and the cavity is, this distance is r by 2. So r by 2 divided by 3. So now I know g. I simply put it over here and see what do I get. So v square will be equal to 2 into g is 4 pi g rho by 3 into r by 2 into r by 2. So what do we get over here? 1, 2, and this 2 gets cancelled out, 2 and 2 gets cancelled out, so I'll get 2 upon 3 pi g rho r square. 2 upon 3 pi g rho r square. So this is v square, and therefore v will be equal to square root of 2 upon 3 pi g rho r square. So this is the velocity when the mass reaches point A. So I hope you have understood that how what I explained to you in the previous slide makes it easy for you to solve these what appear like difficult questions. Fine. Let's quickly move to the last and the third question for this video. And this is related to electrostatics. I have taken one question on electrostatics. This was a question asked in JEE 2012. An infinitely long cylinder of radius r has a uniform volume charge density rho. It has a spherical cavity of radius r by 2 with its center on the axis. So this is the cavity over here. This is the uniform cylinder. The magnitude of the electric field at point P. So this is the point P over here, which is at a distance 2r from the axis of the cylinder. This distance is 2r given to us, is given by the expression 2 3r upon 16k epsilon naught. This is epsilon naught. The value of k, this value k is a constant. This value is not k is equal to 1 upon 4 pi epsilon naught. So that's one thing I want to stress upon or bring your attention to. This k is a simple constant whose value we want to find out. Let's not mix up with this k. Okay, let's proceed. So we want to find out the magnitude of the electric field at point A. So the electric field at point P will be the electric field due to this long cylinder or wire minus the electric field due to this sphere which has been cut out. So if I call this cylinder as 1 and the cavity as 2, then E, the net electric field at point P, will be equal to E1 minus E2, which is equal to. Now this is something you should remember, that the electric field at a distance 2r, remember this distance is 2r from a uniform cylindrical wire. What is the formula for that? It is given by the general formula 2k lambda by t. This is the formula for electric field at a distance d, when lambda is the linear charge density of the wire. And please remember, here this k is 1 upon 4 pi epsilon naught. So E1 is equal to, so what we'll do is we'll find out E1 separately. So let me find out E1 separately. So this is E1 is equal to 1 upon 4 pi epsilon naught into lambda upon d. This is small d. Now d is the distance of the point, so that is already given as 2r. So I'll write down 2r. Now what is lambda? What is the surface charge density, or I should say linear charge density? That is not given over here. But we have been given that the volume charge density is rho. So I can use this to find out lambda. So lambda into cross section area will be volume charge density. I hope you get this. Lambda, that is linear charge density, into the cross section area will give me the volume charge density. So in fact the other way around, made an error over here. Volume charge density into cross sectional area is equal to linear charge density, because this already has volume in it. This is charge per volume, which is pi r square into the length, pi r square into the height in this case. So that will get cancelled. So this is the length. I'll write out length into cross sectional area is equal to lambda. This gets cancelled out. So Q upon L. Yes. So volume charge density into cross sectional area is lambda. So I could write down that lambda is equal to rho into pi r square. Okay, with this now I can write down E1 is equal to 2 4 pi epsilon naught into lambda. Lambda is rho into pi r square upon 2r. So I can see a lot of things will get cancelled out. So let us do that. 2 and 2 will get cancelled out. Then 1r pi will get cancelled out. So I will get rho r over here, and in the denominator I'll get 4 epsilon naught. 4 epsilon naught. Rho r upon 4 pi epsilon naught. Okay, so this is E1. This is E1. Let us find out E2. Now E2 is the electric field at point P due to this sphere, and that formula is kq upon r square. So 1 upon 4 pi epsilon naught, that is k. What is charge q on this sphere? We have been given the volume charge density is rho. So the charge will be into rho into the volume of the sphere, which will be 1 upon 4 upon 3 pi radius cube. Now the radius of the sphere is r by 2. So r square upon 8. 2 cube is 8. And of course this r square has to be there. So that r square will be the distance from the center over there. Is 2r. So 4 pi r square. 4r square. Because this distance is 2r, 2r square is 4. Let us once again, k is 1 upon 4 pi epsilon naught. Q is rho into 4 upon 3 pi r cube by 8 and 4 pi epsilon naught and 4r square. Okay, so again here also a lot of things will get cancelled out. So let us see what we will get over here. I can see 4 pi getting cancelled out. R cube and r square, so I will be left with r. So then in the numerator I will have rho r. Denominator I will have 4 pi has got cancelled. So 24 4s are 12, it's a 96 epsilon naught. 96 epsilon naught. Okay, so this is C2. So now let us find out E is equal to E1 minus E2. E1 is rho r upon 4 epsilon naught minus rho r upon 96 epsilon naught. That will give me 96 epsilon naught as the LCM. 24 rho r minus rho r. So that will give me 23 rho r upon 96. 96 I can write down as 6 into 16 epsilon naught. So if I compare with this formula, there is an error over here. This r should be rho, of course. So 23 rho r upon 16 k epsilon naught. So very clearly we can see here this value of k will be equal to 6. So this is how we can find out or apply the cavity problem solutions to electrostatic fields. I hope this has given you a good idea about how to handle cavity problems related to gravitation and electrostatics. In another video on cavity problems, I will take up questions from center of mass, rotational motion, and magnetic effect of electric current. Thank you.